Flows. Flows are mass wasting processes in which the material behaves like a viscous fluid, deforming internally as it moves downslope. The water content in the material is high enough to reduce internal friction, allowing the mass to flow under gravity. Flows can be rapid or slow and are subdivided into several types. Mud flows are rapid flows consisting of fine-grained sediments mixed with significant amounts of water. They often occur in semi-arid regions where sudden heavy rainfall mobilizes loose debris. The debris is swept into gullies and channels, creating dangerous flows that can travel at high speeds. The lake cloudburst of 2010 and Ladakh is an example where sudden intense rainfall triggered mud flows that destroyed buildings, roads and infrastructure. Debris flows contain a mix of coarse and fine material including boulders, vegetation and soil carried by water. Debris flows can be extremely destructive due to the speed and force. The 2013 Kedarnath disaster in Uttarakhand combined heavy rainfall, glacier burst and debris flow sweeping away roads, bridges and entire settlement along the Mandakini river valley. Earth flows are slower flows and fine-grained, clay-rich, saturated soils that deform and move downslope. They commonly occur on gentle to moderate slopes following prolonged rainfall. Earth flows reshape slopes over weeks or months and can damage farmland, buildings and roads. In India, the Western Ghats and Nilgiri hills experience earth flows during heavy monsoon rains when slopes with clayey soils become saturated. Lahars are volcanic debris flows formed when volcanic ash and debris mix with water from rainfall, melting glaciers or crater lakes. Lahars can travel many kilometers along river valleys, burying settlements and farmlands. The 1985 eruption of Nevada del Ruiz in Colombia triggered a lahar that buried the town of Armiru, killing over 23,000 people. The slopes of Mount Pinatubo in the Philippines and Mount St. Helens in the United States of America are also known for destructive lahars. Solifluction. Solifluction is a specific type of flow that occurs in the periglacial environment where the upper soil layers thaw during summer but rest on the still frozen layer of permafrost. The saturated active layer cannot drain and slowly flows downslope over the impermeable frozen ground. This process forms distinctive solifluction lobes and terraces, shaping tundra landscapes in Arctic regions such as northern Canada, Alaska and Siberia. Creep is the slowest yet most widespread form of mass wasting. It involves the imperceptible downslope movement of soil and regolith driven by repeated cycles of expansion and contraction due to the freezing and thawing, wetting and drying or biological activity like burrowing animals or root growth. Although extremely slow, soil creep can cause significant long-term impacts. Trees or creeping slopes often show bent trunks, fence posts till downslope and building foundations crack over time. Creep is widespread in Darjeeling, Himalayas and Nilgiri hills where slopes are heavily terraced for tree plantation. Complex movements. Many real-world mass wasting events are complex, involving more than one type of movement. A slide may break apart and transform into a debris flow. The 2013 Kedarnath disaster is a classic example of such a complex event where the initial slope failures evolved into debris flow exacerbated by glacial melt and intense rainfall combining multiple processes in one of the catastrophic events. Causes and contributing factors to mass wasting. The occurrence and frequency of mass wasting depend on the balance between driving forces and resisting forces. Several natural and human-induced factors disturb this balance. The first one being slope gradient. Steeper slopes have greater gravitational pull acting downslope. Natural processes like faulting, river incision, coastal erosion or glacial retreat may steepen slopes. Human activities such as road cutting, mining and construction can create artificial steep slopes often without adequate slope stabilization measures. Second one being water content. Water is a key factor in mass wasting. Moderate moisture increases cohesion and surface tension, stabilizing slopes. Excessive water, however, fills pore spaces, adds weight and acts as a lubricant, reducing friction. Heavy monsoon rainfall, rapid snow melt, dam leakage or irrigation can saturate slopes and trigger slope failures. The landslides of the Western Ghats and northeastern hills during monsoon season are classic examples. Geological structure. The type and arrangement of rocks influence slope stability. Layers of weak, unconsolidated materials like clay, shale or volcanic ash are more prone to failure. Plains of weaknesses such as bedding plains, joint or faults dipping down towards the slope act as a natural slip surfaces. In the Himalayas, folded sedimentary rocks with numerous faults and fractures are especially vulnerable. Vegetation cover. Roots bind soil particles and help absorb excess water. Dense forests protect slopes by intercepting rainfall and reducing surface runoff. Deforestation, overgrazing and wildfires remove this natural reinforcement, exposing soil to erosion and slope failure. Many Himalayan landslides can be linked to deforestation for roads, agriculture and settlements. Seismic activity. Earthquakes can dislodge rocks, crack slopes and weaken hillsides. The 2005 Kashmir earthquake triggered thousands of landslides and rockfalls, blocking rivers and roads, hampering rescue operations and causing secondary hazards like flash floods. Human activities. Anthropogenic factors like unscientific road construction, quarrying, deforestation, unplanned urban expansion and poor drainage design exacerbate slope instability, improper disposal of waste and excavation of slopes without reinforcement frequency causes failures during heavy rains.